Hello everyone, welcome back to BC Calculus. In this video we're going to do a differential equation that is specific to something called Newton's law of cooling. It's actually a really cool example that I like to do a lot with my students. And Newton's law of cooling basically is a differential equation where we have the change in our temperature with respect to time. And again, just as before, you guys know that we have some value k, it's directly proportional to this temperature minus this a. All right, and we're going to talk about what the a is here in a second. But let's go ahead and read the question and then solve the problem. It says, you're on vacation in Ocean City, Maryland. One day, as you return to your hotel room, a police officer stops you in the hotel lobby. She informs you that a dead body was found in one of the rooms while you were out and that foul play is suspected. The police officer would like to determine the time of death, but the Ocean City coroner is out of town and cannot be reached. It seems that you mentioned to the desk clerk that you were on vacation to recover from your calculus course. So, of course, the police officer is going to ask you guys to incorporate your calculus knowledge for your expert help. The police officer takes you to the morgue, which is near the hotel. She tells you that the body was discovered at 4 p.m. with a temperature of 30 degrees Celsius, in a room where the temperature has been a steady 20 degrees Celsius for many hours. So this is going to be our determinant. This is going to be our A value. This is going to be what the A is. A is going to be what the room temperature was. So what was the temperature that was housing the body? Because this is constant, so the A is going to be 20. When the murder is committed, the body originally 37 degrees Celsius, and this is the eternal degree for a human body, cools according to Newton's law of cooling. Suppose that after 2 hours, the temperature of the body is now 35 degrees Celsius. Assuming that the rate of change in the body temperature is proportional to the difference between body temperature and air temperature, which we get over here in this one, we'll use that assumption to help approximate the time of death. So we want to know what's going on with our time of death. So a couple things that we know is this, that the body was discovered at 4 p.m. with a temperature of 30 degrees. We know that the original was 37 and that at time equals 2, at 2 hours, the body was 35 degrees Celsius. Now, we could take the equation that we just had at the very top, which you guys see as right here as we wrote it, and we can solve this differential equation. All right, we can solve this differential equation by going dt over t minus a is equal to k dk. So separation of our variables. And when we do this, we're going to get the natural log. We're going to integrate both sides. We're going to get the natural log of the absolute value of t minus a is equal to kt plus rc. Now, you guys know as well as I do that we can add e to both of these to get rid of the natural log. And we're going to get that t minus a is equal to e to the kt times e to the c. I've already showed this example. I showed you guys how to do this in one of the previous lessons with differential equations. This was the application part of how to solve this right here. And so remember that this is our new constant, right? This is our constant. So I'm going to call this constant our big old C. And the reason we normally call it A, but because we have an A here, we're going to do that. So we're left with this. T minus A is equal to C e to the kt. Now, we got to solve for these values, right? We need to know what the C is and we need to know what the K is. That's what we always do in the previous examples, is figure out what the C is and what the K is. Well, we can find the C by knowing that T minus A equal to C e to the kt. So let's rewrite that up here for us. So when we're looking at time equals 0, because that's really easy, right? At time equals 0, we were told that the body, this temperature, the T, the big T, is equal to 37 degrees Celsius. We know that the A is going to be 20 degrees Celsius. So we can easily find C by taking 37 minus 20 is equal to C e to the 0 power. So C is just going to be the difference in the temperature that the original body was minus what the room temperature was. So C is going to be equal to, in this particular example, 17 degrees. So we can go ahead and write that T minus A is equal to 17 e to the kt. So now we know that a time equals 2 hours. A time equals 2 hours. We can say that our temperature, now our temperature of our body is actually going to be 35. So we're going to go ahead and now type in or write 35 for our new temperature, because this is the temperature of our body, right? As through time. So temperature of our body with respect to time. So let's look at it this way, and we're going to get that this is 15 equals 17e to the 2k. And at this time, we can go ahead and divide by 17. And you guys know the next step, because we've done it many times before. We can add the natural log to both sides. When we add the natural log to this, we get the natural log of e to the 2k, which just becomes 2k. So we get k is equal to 1/2 the natural log of 15 over 17. So now we can finally say that our equation that we're going to have now is t minus 20 is going to be equal to our c, which is 17, e to the 1/2 natural log of 15 over 17 t. Okay. Now we can figure out our time, because it tells us that our body was found at 4 p.m. at 30 degrees Celsius. So we can go ahead and write out 30 minus 20 is equal to our same function. And we have to solve for t. We have to solve for t here. So we're going to get 10 over 17 e to the 1/2 natural log of 15 over 17t. We're going to add the natural log to both sides again. This is definitely a calculator problem. I mean, this is 100% a calculator problem, because it gets really crazy. And so we're going to get natural log of 10 over 17 equals 1/2 the natural log of 15 over 17t. And then, and you guys could see what the k value is. Like, this is another thing that I, just could say. We could use the decimal equivalents to this if you wanted to. So I'm going to write this out, but you really want to try to not approximate to the very, very end of this. But this number right here ends up being this value that you see right here. But we're going to go ahead and do this. And when all said and done, when you find t, so you're going to take this number and divide by this number, you're going to get the t is 8.479 hours. Okay, so this is an hours since 4 p.m. And that's why that 4 p.m. was given to us. All right, so students were like, why don't you plug in t for 4 p.m.? Now we want to use that since 4 p.m. So this is the time that the body has been dead. I know this example is morbid. That body has been dead since 4 p.m. So you have to go backwards. You have to go backwards from 4 p.m. approximately 8.5 hours. I mean, let's be kind of, understanding that to the point for what we're going to do here. So we're going to go back 8.5 hours, and we're going to get that this death approximately occurred at 7:30 a.m. in the morning. Okay? So that is another good way of showing you guys differential equations using Newton's law of heating. So approximately at 7:30, the body unfortunately passed away. So there you go, and that's it for this lesson. I will see you guys back in the next set of videos. Take care.